In this lecture, we will be discussing the networking models used in the industry. Everyone knows this, but for those who don't, there are two networking reference models that are widely talked about: the TCP/IP model and the OSI model. The aim of the video is to summarize and be a one-stop destination for the networking model discussion. Also, note that these models are separate entities. It's just that over time, one was favored over the other for different use cases. The most important question: which one came first? The internet has many answers to this, and many confusing answers as well. A lot of people say that the TCP/IP model was devised 10 years before the OSI model, but many references state this as wrong. For example, the Communications and Networking Guide by John Coley states that the OSI model was designed before the protocols and the TCP/IP model came after the protocols. However, the dates say otherwise, as the TCP/IP model was stated by Cerf and Kahn in 1974, and the OSI was stated by Day and Zimmerman in 1980. But the work on this was claimed to have started back in 1970, which is probably the reason for this confusion. This is now more like the story of the chicken and the egg. Which came first? I would like to say that these were models that were designed or drafted in parallel by different entities. The pictures speak for themselves, and these are how the models are plotted. What do these models look like? A 7-layer OSI model on the left and a 4-layer TCP/IP model on the right. How they map and relate to each other is also shown, where the top 3 layers in the OSI model are summarized by 1 layer in the TCP/IP model. The transport layers map to each other, and the network layer maps to the internet layer. The data link layer and the physical layers in the OSI are summarized as the network access layer in the TCP/IP model. Let's start with the OSI model. The OSI model was more like a reference model. It was not for individual protocols to be mapped, but one that stated what each layer was supposed to do. It also helped standardize all the networking protocols. Layer 1 of the OSI model is named the physical layer because it is responsible for the transmission and reception of wire-level data. For example, the physical layer is where it is dictated how bits are represented across a specific networking medium. Layer 2 of the OSI model is named as the data link layer. This layer is responsible for link establishment and termination. It is also responsible for frame traffic control, sequencing, and acknowledgement. Error checking also happens at this layer. Layer 3 of the OSI model is named the network layer, and this is where the routing of network traffic begins. The network layer not only makes the traffic routing decisions, but also provides traffic control, fragmentation, and the most important part, logical addressing. When I say logical addressing, I mean Internet Protocol addresses. Layer 4 of the OSI model is named the transport layer, and it is responsible for message segmentation, acknowledgement, and traffic control. It also takes care of session multiplexing. The transport layer has the ability to perform error detection and correction, which is retransmits, which no other layer has. It can also perform message reordering to ensure the proper message sequence. A reliable message channel can be ensured depending on the specific transport layer protocol used. Layer 5 of the OSI model is named the session layer and is responsible for session establishment. It takes care of maintenance, termination, and also has the ability to have multiple devices use a single application from multiple locations. Layer 6 of the OSI model is named the presentation layer. It is responsible for character code translation. For example, ASCII and Unicode and many others. It also takes care of data conversion, compression, and encryption. Layer 7 of the OSI model is named the application layer and is responsible for a number of different things. It depends on the application, of course, but some of these include resource sharing, remote file access, remote printer access, network management, and of course email. There are many others beyond the list that I have already stated. On the other hand, the TCP/IP model avoids repeating the work already done by some other standards body or vendor consortium by simply referring to the standards or the protocols created by these groups. Let me give you a real-world example here. You buy a replacement for an appliance but are still able to plug into the same socket that was set up before. This is because the vendor followed the standards. Same is with networking. The vendors follow the TCP/IP nowadays for their design. Let's discuss the TCP/IP model. The first layer is the network access layer. This layer combines the physical and the data link layer of the OSI model into a single layer. This includes frame physical network functions like modulation, line encoding, bit synchronization, frame synchronization, and the obvious error detection. The internet layer is the next layer and is associated with the network layer of the OSI model. Functions such as traffic routing, traffic control, fragmentation, and the logical addressing, which is IP addresses, is handled at this layer. The transport layer is the next layer and is typically related directly with the same named layer in the OSI model. Functions such as message segmentation, acknowledgement, traffic control, session multiplexing, error detection, and correction happens at this layer. The application layer is the highest layer in the TCP/IP model and is related to the session, presentation, and the application layers of the OSI model. The application layer of the TCP/IP model is used to handle all process-to-process communications. These communication functions were carried out by multiple different layers when we referenced the OSI model. Let us look at a real-world example over here for the OSI model. If you want to compare the TCP/IP model, just club the layers together. You decide you want to connect to a web server at an IP address for say 10.0.12.34, which is within your organization but not on your local network. You type this address into your browser. This is the layer 7. With a website connection, nothing usually happens here, but format translation of the way data looks may be done in some cases. This is the layer 6. The request is sent via a call to an API, application programming interface, which issues the command necessary to contact the server at that address that you specified. This is layer 5. TCP is used to create a segment that will be sent to the IP address 10.0.12.34. This is layer 4. Your computer creates an IP datagram encapsulating the previously created TCP datagram. It then addresses the packet to 10.0.12.34 but discovers that this is not on its local network. Instead, it realizes here that it needs to send the message to its designated routing device or default gateway, which is at an IP address 10.0.43.21. It hands the packet to the driver for your Ethernet card, the software that interfaces to the Ethernet hardware. This is your layer 3. The Ethernet card driver that has received this information forms a frame containing the IP datagram and prepares it to be sent over the network. It then packages the message and puts in the address for 10.0.43.21, which is the default gateway in the frame. This is your layer 2. This frame is then sent over the twisted pair cable that connects to your local area network. I'm ignoring the overhead collisions and so on here, but then I also ignore the possibility of collisions with the plane itself. But this is what layer 1 is about. The reverse happens at the other end as well, therefore completing the whole transaction. Don't forget to check the Extra Bytes lecture for other references.